this video, we're going through another activation function called Softmax. Softmax is actually very important. It's even used in ChatGPT as well. And then another thing to keep in mind is Softmax can only be applied to the output neurons because it applies to all of the neurons at the same time. It doesn't separate them. Like for example, something like sigmoid, it goes through each neurons individually. And then, so let's first draw our neural network again. So for example, I have 2 or 3 inputs, and then I have one hidden layer with 2 neurons, and then I have my output that are going to be 3. So, okay. So the way it works, if there is a sigmoid is going to be here. The activation function is going to be applied to the neuron itself. So whenever a neuron calculates whatever it has to calculate, then it will go through the activation function sigmoid, and it will give it a probability between 0 and 1. And it cannot reach 0 and 1. But then when we are talking about something like Softmax, we do have a 1 because we don't have this anymore. Let me just remove it. For Softmax, you have all of your output sent to one activation function. And why is that? Because when each neuron has its own independent activation function, like sigmoid, they don't know about the other neuron, okay? Each one of them individually come up with the number. So you might have 90% chance for 2 of these outputs, or one of the outputs can be 95% and another one can be 50%. So when it is adding up, it's going to be more than 1. So for sigmoid, you're not adding them together. Each one of the neurons are going to work individually. But then when you're doing Softmax will take all of the values, all of the raw values, or it is called logit. It's going to take all of that and then send it through Softmax. But when you're adding all of these values, like for example, if this one is 0.5, this one is 0.3, this one is 0.2. Okay, when you're adding them up together, it's going to give you 1. So this is an actual 1, not traveling toward 1, but when you're adding all of them together, it will give you 1. Because now you're not comparing if it's this or if it's the other one. Because here, you're not doing binary as you're doing with sigmoid. You are comparing all of them with each other. Like for example, here, right now we have the highest probability for this output. Now that we talk about this, so this is the basic idea of Softmax. What it does is just there is one activation function and that receives all of the raw output will give you a probability. But since it is comparing it to all of your outputs, since it is comparing it to all of the other outputs, when you're adding them together, you're going to get 1. Okay, so this is the basic idea of Softmax. Now let's go more in detail and see what's happening. So till now, everything is good, okay? Output can come up with a number. That number is going to be compared to all of the other outputs, and you're going to get your probability, okay? But it's not that easy because the first time that you're passing them through Softmax, that is not going to be the perfect value. You still have, when you're comparing it to the actual value, you're still gonna have error, and you want to correct that error. And we already talked about this in neural network. When you want to learn, you're doing backpropagation, okay? Backpropagation use gradients in order to learn. So backpropagation is using gradients. So backpropagation goes and update each one of these weights. So each one of these are going to be more or less important when you're getting the input. So then your output is going to change until it will matches to your real output or very close to it. And for that reason, for those weights to be updated, you're using something called gradient. Gradients, so for example, if you have a gradient here, it wants to go to the lowest point that's possible. So for example here, this is the lowest point that is possible, right? Because it wants to reduce the it wants to reduce the amount of error. But this is not the only gradient that we are using for updating our weight. We are using activation function gradient as well. And also we said that gradient is basically just the partial derivative. That means that it will look at, for example, here you're very steep, so it knows that it's supposed to go down, or it's supposed to go down this way. And then when you're here, it knows that it's supposed to come back because it's very steep. And then whenever you're at a place that is flat, then the learning kind of stops or slows down. So now you see that we have problems with flat lines because our learning happens through gradients. Gradients are basically derivatives. Derivatives doesn't do well with flat lines. It does best when it is steep. The learning will happen when it is steep. We're not only using the loss function in order to calculate the gradient and ultimately update the weights. So when we are updating Softmax, imagine, this is not how Softmax works, but imagine I have, for example, 5 here, 3 here, and 2, like the same numbers that are there. And then for example, I want to calculate the probability of the first one. What I do, I put 5 up there, and then I put 5 plus 3 plus 2. So what I'm getting is 5 over 10, which is going to be 50% or 0.5. So what is the problem with this? As we talked about, flat lines are not good. But then when you want to plot something like this, you're going to plot it like you're going to get a flat line. Okay, oh sorry. You're gonna get a flat line. And what is the problem with flat line? Flat line means that no learning is happening. So if we want to use Softmax as a normal, if we want to use Softmax as just like a simple probability, we're gonna have this problem. The neurons before the output can actually produce negative numbers, okay? So negative numbers is going to make this whole process a little bit more complicated. But how we fix this problem is we are using exponential. We are using exponential to calculate Softmax. I'm not going through the formula for it, but know that we have exponential both at the top and the bottom, okay? So when we have exponential, first of all, when you have exponential, then you won't have a straight line. Your line will be curved. Your line will start being curved. When you're using exponential, your line will start being curved. And then when you have curved line, as you can see, now learning can happen. So this is one of the things that exponential helped to solve in Softmax. So we cannot just get the raw data from output and just say, okay, this is the probability, and have a very simple probability we can have a very simple probability instead of Softmax. We get all of the raw output and say, okay, this is the number. You're gonna have problem learning because you're gonna create in a straight line. And this is not the only problem that exponential solves. The other problem that exponential solves is sometimes you will get a negative number here. If you get a negative number here, it's going to make everything complicated. But if you pass that negative number through exponential, exponential will transform it into a small number. So then now you can actually add all of them together, and the result is going to be 1. Okay, And then another question you might have is, what, you would just change the number? Even though you're changing the number by passing it through exponential, what is happening is that all of the numbers are going through exponential. Okay, so basically you are changing the dimension of the data. What I mean by that is you're looking at your data from another angle. So let me give you an example. For example, there are two people standing in front of me, and I'm looking and I only see one person. Okay, and then after that, and as long as I stay in this dimension, as long as I'm looking at it from this angle, I will only see one person because the other person is hidden behind the person that I'm seeing. But I'm going to move and I'm coming here and then I'm looking here and I see that, oh, there are actually 2%. And if I want to divide them, I can just draw a line and divide them. That's the same idea with the exponential. You still have the same relationship between those numbers because they're the same numbers. All of them are just going through exponential. But what is happening, you're looking at it from another dimension and you're able to learn from that number. And since you change the dimension, change the angle that you're looking at those numbers, now you get more information from that data. Now you can actually backpropagate and you can learn.